In this engaging video, we are taking a deep dive into the world of geological forces and rock deformation, using the powerful tools of BlenderGis. Join me on this scientific adventure as we unveil the fascinating history written in stones. Our destination? The shear zone just north of Mount Titlis. We will set our sight on the vertical cliffs of Mount Schwarzwald. The shear structures created by the relentless forces of tectonic rock movements are here vividly exposed over several hundred meters. This offers us an up-close view of the rock deformation in remarkable details. This shear zone tells the story of recumbent faults pushed several kilometers northward, forming the Helvetic folded stress belt. The thrust or displacement zone is the result of powerful shear forces propelling the colossal Rotsandknollen thrust fold northward. The overriding rocks, which originated to the south of the Grausstock rocks, fractured on its northwest push into several subunits, creating a complex recumbent fold structure. Here, nature has crafted small-scale fold and fold structures within a 200-meter thick displacement zone, revealing a mesmerizing geological showcase. During the alpine compression, hard limestone and soft marl horizons were bent and sheared under extreme pressure and temperature conditions. Folding and thrusting occurred under a thick tectonic overburden at a depth of approximately 10 km at elevated temperature and pressure. The hard limestone underwent brittle deformation, while ductile mechanism operated in the softer marl horizon. The tectonic bending led to tight folds with distinct hinge zone and extreme space compressions. Under the overburden, very tight folds formed with areas of intense space tightening. These areas are represented by overlapping meshes in our model. In nature, two distinct deformation styles are observed in these hinge zones. In the synclinal hinge zone, a 200-meter thick shear zone developed with imbricated thrust packages, extremely tight folds, bed parallel slip zones, and a sharp basal thrust cutting through the flat-lying cementstone marl, separating an unfolded lower zone from an overfolded upper zone. In the anticlinal hinge zone, the core of the Rotsandknollen fold structure split into several tight folds. During the northwards displacement, a basal thrust plane developed, separating the relatively undeformed normal limb of the Grausstock fold from the overturned Rotsandknollen fold, which further split into several substructures. For a more in-depth look at this fascinating structural marvel, please refer to the referenced video below. Let's take a closer look at some fascinating small-scale features found in two locations along the shear zone. Zone 1 displays a variety of deformations, including different types of sliding, stacking and folding in rock layers, which reveal the complex process acting in a shear zone. Rocks moved along different gliding planes. Hard, thick and sturdy limestone layers have been stacked in a northward direction, moving along a 30-degree sloping thrust fold, cutting across the rock layers. In contrast, many bed parallel gliding planes are seen where softer rocks have slid against each other. In between the bed parallel gliding planes, rocks are bent and folded. Tight and isoclinal folds are observed in more homogeneous units. V-shaped kink folds, so-called chevron folds, occur when densely layered anisotropic formations are deformed. Chevron folding occurs when regular alternation of rocks with varying hardness are bent. The competent stiff limestone beds tend to kink and fracture radially at the bend, whilst the softer marlioschist layers deform and flow in a plastic manner. Thin limestone beds intercalated with marls were deformed into flexural slip folding pattern where the angles between the limbs are generally 60 degrees or less and the fold limbs are nearly flat. Let's take a look now at the shear zone beneath the leading edge of the Rotsandknollen recumbent fold. The overturned limb of this thrust fold is severely imbricated and thinned out. The shear zone exhibits here intense folding and rock sliding within the cementstein milestone. The fine clastic rock units is here remarkably thicker, possibly due to tectonic repetition or initial thicker sediment deposition. The deformation is striking. Rock masses were gliding parallel to each other. Hard limestone rocks are tightly folded into isoclinal folds with parallel limbs and narrow hinge zones. This suggests long-lasting extreme shear forces acting during the northward movement of the Rotsangnollen megathrust fault. In summary, our journey through the shear zone near Mount Grausstock unveils the story of intense tectonic forces shaping rock layers into tight folds, bed parallel shear planes, and thrusts. The shear zone is a vivid testament to powerful tectonic forces putting in place the stack of recumbent faults making up the Helvetic thrust and fault belt. Mount Schwarzhorn shear zone is one of many examples one can explore in this mountain belt, the architecture of which is shown in this block diagram. I hope you enjoyed this exploration into the mountain building process. If you found it fascinating, please consider giving me a thumbs up, subscribing to my channel for more exciting content. Thank you for joining me on this geological adventure.